Now we have the expression d divides n. Now we need to prove this. So this is our claim, and we need to prove this. Now let's make a line. Okay. Now to prove this, we need to see a couple of things. First, so by the way, the proof won't be that rigorous, because if you want it to be rigorous, the video will be long, and I don't wanna write a long proof with a tablet, so we are just gonna use some common sense or whatever. So let's start. Now, let's first see what this means. D divides n. So we have values that divides n. So for example, if we have 6, okay, the divisors of 6 are 1, 2, 3, 2, 3, and 6, right? All of these values divide 6. So our claim is that totient of 1, by the way, this is the totient function, which I'll explain later. So me first write this totient of 2 plus totient of 3 plus totient of 6 is equals to 6. Our claim is this. Is this true? Yeah. Totient of 1 is 1, 2 is 2, 3 is 2, 6 is, I think, 2. I think I made a mistake because totient of 2 is 1. So let's delete this. Yeah. And 2 plus 2, 4, plus 1, 5, plus 1, 6. This is true. Now, let me explain the totient function for those who don't know. This value, this totient of a value, so totient of some value k is equals to, this is the representation. So this is for prime p. This is how they calculate the totient function. And this is also true. I'm not going to prove this. We are not going to use this, but this is a way to calculate the totient function. Or another way would be that you write k, okay? You write the amount of values that are relatively prime to k that are also up to 1 to k minus 1. For example, if k is 8, we are looking for values that are relatively prime to 8. So 1 is relatively prime to 8. By relatively prime, we mean that GCD of 1 and 8 is 1. So GCD of 2 and 8 is 2, so 2 is not relatively prime. That's why we don't write 2. 3, yeah, 3 is relatively prime to 8 because only 1 divides these 2. Minus 1 also divides, but we are looking at positive values, positive integers. 4, nope. 5, yes. 6, no. 2 divides both of the values. 7, yes. So we have 4 values, so totient of 8 is equals to 4. Totient of 8 is equals to 4. Okay, now let's do the proof. Now, we need to show a way that we are going to be able to represent the divisors of n. So, realize that. So, okay, assume n is equals to this. 1, 2, let's say some value m, pm, em. So p is prime, right? We can represent every value with primes, with the multiplication of primes. I am again not gonna prove this. This is induction, or you can swap well ordering principle. It's up to you. Now we are assuming that we know this knowledge. We can represent every integer, positive integer, with primes being multiplied together. And this is also known as unique factorization, which also works in integers. Now, so to represent every divisor of n, we can use this notation. I'm first going to write it in this form. K equals to, wait, we need to use product first. 1 to m, sigma, and then j equals to 1 to ek, and then pk ej. Now it might be hard to visualize this, and yeah, it's also hard, I know, but let's do an example. Let's say n is equals to, let's say 6. Actually 6 is a good value. No, let's use 8, 3, 24. Yeah, this is better. I changed my mind. Let's use 12. Okay, so the divisors of 12 are 1, 2, 3, 4, 6, 12, right? And we can write this as using this notation: 1 plus 2 plus 4, 1 plus 3. Now this notation turns into this if n is equal to 12. And then when you expand the parentheses, you are going to see that we are going to get exactly the same values that are in here. So this actually works. And this is also equals to, we can also write this as 1 plus 2 to the 1 plus 2 to the 2 multiplied by 1 plus 3 to the 1. Yeah. Now, just pause the video, try to understand this. And of course, I'm also not going to prove this right now, maybe in later videos. Maybe I might also prove unique factorization in later videos. But for now, we are assuming we know these lemmas or proofs. Now I'm going to clear the board again and let's continue. Okay, now that we proved that, let's work on an example. So let's work on 12 actually. So our claim was this, right? We know our claim is this. Now for 12, we proved that the divisors can be written as 1 plus 2 to the 1 plus 2 to the 2, 1 plus 3 to the 1. Okay, so these are, when you expand the parentheses, you are going to get all the divisors summed up together. Let's come back to our original statement. We need to represent totient of D, right? Summed up together. So what we can do is we can write actually this statement right here. Now, oops. Can I carry this up? Yes, of course I can. Nope, I can't. Whatever. So realize that when we take totient of each value right here, right? We took totient of those values, and then when we expand the parentheses, right, we get this. Now, this can be also written as totient of what? D for D divides N, which was our original claim. So yeah, we can convert this into that basically. And you can pause the video, just think about this, because it's not easy to understand. Okay, so I hope you thought about this. This is not easy to see. It took me kind of hours to prove this, but whatever. Now we are gonna use another lemma, which I won't prove in this video, but in later videos I might. And the lemma is totient of p to the m for prime p is equals to p to the m minus p to the m minus 1. Oh, oh, why can't I just write 1? Okay, yeah. You can just try to prove this. This is, I think, hard. At least for me, it was hard, but you might be able to prove it. And yeah, this is always true for, of course, integers, prime p, and m is also an integer, positive integer. Now, what we are going to do is we are going to apply this into this. So what I mean is, let's put a big comma here. Let's take the first multiplication. Now let's take this. Okay, let's apply what I wrote in here. This thing turns into 1 is always 1, so we are always going to have 1 here. Plus 2 to the 1 is going to be 2 to the 1 minus 2 to the 0, right? So we can write 2 to the 1 minus 2 to the 0 plus 2 to the 2 is going to be 2 to the 2 minus 2 to the 1, right? Realize that this cancels out that, and 2 to the 0 cancels out 1. So eventually we get 2 to the 2. So basically this whole thing is equals to 2 to the 2. Similarly, the second part, this part is gonna be, yeah, you might have guessed it, it is gonna be 3 to the 1 when you do cancellations. Okay, so what we get is 3 multiplied by 2 to the 2, which is 4, and 3 multiplied by 4 is equals to 12. So this thing is indeed 12. Now, when we say we cancel out these values in here, it's not rigorous enough, which you will, if you want to prove it rigorously, you will need induction or WAP, well ordering principle. I generally use WAP, but I'm not going to prove it right now. I'll leave it up to you to prove it on your own. And yeah, this is basically how we prove it. So we are done. We basically get actually the prime factorization of 12. So for any value, for other values, so let's do an example actually. Let's do 18, 9 multiplied by 4, 36. There are lots of divisors, but we can do 36, yeah. So let's say n is equal to 36. So we prove that this whole thing, we can write it as totient of 1 plus totient of 2 plus quotient of 4 multiplied by quotient of 1 plus quotient of 3 plus quotient of 9, because 9 multiplied by 4 is 36, and we just wrote primes that are smaller than, so 9 is 3 to the 2, we wrote 3 to the 1, we wrote 1, we wrote 2 to the 2, we wrote 2 to the 1. You can write 1 as 2 to 0, but then this lemma won't work in there. That's why I am keeping 1 as 1 instead of like 3 to the 0 or 2 to the 0. So this is going to be 1. And when you do the cancellations again, this is going to cancel out, this is going to cancel out, this is going to lead to 2 to the 2. This is going to cancel out again, this is going to cancel out, this is going to lead to 3 to the 2. When you multiply these two, you get 36, which again is not a counterexample, and our proof is basically correct. So this is how we prove it non-rigorously. And yeah, if you have any question, please leave a comment and have a great day.